go to forecasting, forecasting. You ready? We're on chapter 15. Some of these are so easy, and you're going to go, oh my gosh, we'll spend too much time on it, it's just so easy. And some of them start to get difficult. Moving average, I'm going to break it down and make it real easy. We're going to go fast because it's just too easy. Odds of having a quiz on moving average, I don't know. I mean, a final. Center moving average, we're going to skip it first because this starts to confuse people. It depends if you have an odd amount of data or an even amount of data that you're being asked to do a center moving average on. That's what makes that one hard. Weighted moving average is very easy. We actually use something just like weighted moving average when we were finding the expected time on that project scheduling. When we were given 3 different times, we put a bunch of weight on the most likely time, then we added the pessimistic and optimistic. That's just like using a weighted moving average. That's exactly what we're doing when we calculate that expected time for an activity. Exponential smoothing is pretty easy, but some people don't like it. Trend projection starts to get a little hard, but I break this down and make it easy. But the trend projection with seasonality involved is very hard. This is where everybody starts to stress out. And, so I wait until the evaluation is done. Mean square error. This is throughout this whole thing. Remember how economic analysis was every one of our service ways of learning? Mean square error has to do with all this. This is what we use to determine which one of these are connecting with our data the best, and then we say that's the one we want to use to make our true forecast. So at first, you're testing these with some data that you're thinking about forecasting. And you're calculating, and there's 3 different error calculations in your book, but I'm going to highlight just this one for the final exam. And this is the one I use the most and found the most accurate and the most useful. But we're maybe testing 2 or 3 of these on the data, calculating the error, then select the one that fits best, then make our forecast. See the order of what we're doing here? In real life, that's exactly the case. In my case, in all accounting majors, this is in your future, period. When you are managing an accounting office, or you are working on budgets and all kinds of forecasts, and all your numbers start with your estimations of the future. And this is where I always use this to do my estimations of the future. And this is what will create some real accuracy in your forecast, is this, unless some unusual economic situation takes place, like the market crashing in one day. What happened today, by the way?
800 points down.
800 points? By the end of 4 o'clock, it was 800? You guys, when you have retirements in the market, when you're all working full time, you'll start feeling the pain of a day like today. Because you'll get online and you'll put in your password, you'll look at your account or your retirement, and you'll go, oh my God, I just lost $10,000 today. What just happened? And you'll start to pay attention. And I've been paying attention every day since the 1980s. Because once you experience a loss, you pay attention. You ready? Where do we start with moving average here? We're going to slide 9. In this example, it's asking for a 3-period moving average. It's just this easy. You ready? If you want to forecast the future, which would be period 11.
Can you move it over a little bit so I can see what slide you're on?
No, I don't know. I haven't figured out how to do it this new computer
You
yet.
just don't make it.
I'd have to go in and change the settings, wouldn't I?
No, you just don't make it all the way big and just like.
Oh, like this. You mean do this?
Yeah.
Okay,
But
let
then
me stretch it
still-
out. Whoop. Wait. Does that work?
Yeah.
What about there? Can you still see everything?
Yes.
How far can I go this way? How's that? All right, you ready? If the instructions say use a 3-period moving average, then and forecast the future, which would be period 11, you're using the most recent 3 periods before the period you're forecasting. Let me repeat that. In a moving average, you're using the periods of however many period moving average you're being asked to do of the periods before the period you're forecasting. Say it again. Okay. Let me use period 8 as an example. I'm going to say it again in a different way. It already has a number, but you're being asked to forecast period 8 as if a number is not there. Which periods would you use in a 3-period moving average if you're forecasting 8?
5, 6, and 7.
That's right, the 3 before it, 5, 6, 7. You got it. That's exactly. So you put in the word you want, but you got the logic. What if I said this is a 4-period moving average, and I want you to forecast period 9? What periods would you use?
5, 6, 7, 8.
The 4 before it, exactly. Now, you get a quiz in front of you, and you got data in front of you. The most common mistake on moving average, I mean a final, not a quiz, is that if I'm asking for period 9, let's say it's a 3-period moving average, there's a good percent of you that are going to use periods 7, 8, and 9, add them together, divide by 3, and give you the forecast of 9, when it should have been the previous 3 periods, not including the period I'm asking for the forecast. Everybody hear that? The periods before. So that's what will clear up what you're about to see here. Let me go to the next slide. Whoops. All right. Do you see this forecast right here? It looks like it's for period what? 3. But it's not. That's period 4. This is a 3-period moving average. You can't get a forecast for period 1 because there isn't 3 periods before it. You can't get a forecast for period 2. You can't get a forecast for period 3. Period 4 is your first forecast that you could even get because it's the first one that has 3 periods before it. But here is just this Excel spreadsheet has this as the period that you're asking for plus 1, or the number of periods plus 1 or something. So really, even though this is number 3, this is number 4 because you got to add 1. Now, I didn't make this slide. If I did, that would really be right there, which I think makes more sense. Because it's trying to show you that the first forecast is in period 4 because you're asking for a 3-period moving average. This is a, let's say this is a 5-period moving average. Your first possible forecast, even though you have 20 years of data, 20 periods, your first possible forecast in a, what did I say, 5 periods, right? Would be in which period? 6. It's the first one you have 5 previous periods you could use to do a forecast. So it has to be in 6. You get it? Don't put it in 5.
So on the final, will yours be moved down?
You won't even have an Excel spreadsheet. You'll just have something, if this is on there, you'll have data like this.
Okay.
And then you may be asked to, hey, do a 3-period moving average and calculate an MSE. We're not there yet, what that means, but that will probably be like the question. And then it will say, now do a 3-period weighted moving average and calculate MSE, and tell me which one of those fit that data the best. That's where we're headed. You know, it could be with any of these. Here's the data again. Now do an exponential smoothing with a smoothing constant of 0.3, which you're about to learn how to use. It's very simple. And compare it to a weighted moving average, 2-period, and here are the 2 weights. You calculate the MSE for both. Which one would you recommend? That's where we're heading. You got to know how to do any of these up there, and how to calculate this on any of these, so, and what it means, what you're looking for when you calculate this, to know which one's better. I'll jump to that right now. Whichever one has the lowest mean squared error is the better forecasting technique for that data. The lowest. If you're comparing 3 or 4 different techniques, the MSE with the lowest is the one you want to use to forecast the future. So all these techniques are forecasting for periods we have actual data already for, so we can calculate how well it works with the data. So if I said, hey, do a 3-period moving average and calculate MSE, I'm not asking you to forecast the future. I'm asking you to do a forecast for every period you have actual data for that you can, and then calculate MSE. 3-period moving average, you told me the first period you could calculate a forecast for was 4. So you'll have a forecast here, and 5, and 6, 7, 8, 9, and 10. But you'll have no forecast for 1 through 3. Then you will compare that forecast for 4 with the actual data for 4 and find that difference. Same with 5, 6, 7. Every period that you're able to do a forecast for, that you have actual data, you're finding the difference. And it's that difference that will lead you into calculating this to determine which one fits better. And that's why you're first doing forecast with comparing it to data that you already know the answer to, so you can just see if it fits the data well. So you know how well it will work with the future. So, let's talk about it. 3-period moving average is just like it sounds. Add the 3 periods before the period you're forecasting, divide by however many periods to find the average, there's your forecast. So if you take 110 plus 115 plus 125 divided by 3, you'll see that it's 116.7, and that's period 4's forecast. Now period 5, just shift everything down 1. The periods before period 5 are 2, 3, and 4, so add 115, 125, 120 divided by 3. There's your forecast for period 5. Shift down, and so on, and so on. Does everybody get it? So to make sure you get this, how many forecasts would you have? Let me go back because I want you to be prepared for a quiz. How many forecasts would you have to compare with actual data if you were asked to do a 2-period moving average?
5.
I see more than 5. 8. Your first one would be where? That's right, because you've got to have 2 periods, add together, divide by 2. There's your forecast for 3. Shift down, shift down, shift down. You would have 8 forecasts. All right? If I asked you to do a 5-period moving average, how many forecasts could you compare to actual data? 5, possibly? That's right, 5. Because you have to have 5 pieces of data to get the 5-period moving average, and you're forecasting the next period, which is 6. Shift down, 7, 8, 9, 10. You're absolutely right, there'd be 5 forecasts to compare. It doesn't matter. Some of these you'll have 4 forecasts. Some of these you'll have 6 forecasts. Some of these you'll have 8 on the same data. But when you get to do this calculation, MSE, you're dividing by the number of data you were able to use, so they all come out to an MSE that are similar to each other, where you're not dividing them all by 6 or 7 or 8. When I said you were using a 5-period moving average, you said there'd be 5 of these. When you get to the end of this, you're dividing by 5 to get to the MSE. We got another step in between. But then you're comparing it to another one, which may have 8 forecasts you're comparing. So you're dividing by 8, and the MSEs now are apples to apples. Okay? And then you compare those and determine which one's best. It would be whichever one has what kind of MSE?
Lowest.
The lowest, exactly. That's the main thing you gotta remember. The lowest MSE is the best forecasting technique for the data that you're thinking about using it on. Okay? All right. Let's get to weighted moving average. Slide 38. I actually like the book example better. Let me see what this looks like. Here's the question might be, I want you to look at here. We have 0.1, 0.3, 0.6 being multiplied by the actual data here. So this is an example of a 3-period weighted moving average. Now here's what the question will look like. There'll be the data up there. And it will say, what are we forecasting here? It looks like we're forecasting period 10. It will say, forecast period 10 for this data using a 3-period weighted moving average. The words 3-period mean you have to use the previous 3 periods for whatever it is you're being asked to forecast. So we're using 9, 8, and 7, right? Then the question says, apply the following weights as such. 10% to the oldest piece of data, 60% to the most recent piece of data, and 30% to the middle piece of data. So what that means is, if we're forecasting period 10, the most recent data would be period 9, we apply 60% weight. The oldest data would be period 7, so we're applying the 10% weight. And then the middle one, we apply 30% weight. Does everybody get how you interpret the weights, applying to the data, and whatever data you're applying it to, you're forecasting the next period. All right, I want to make sure you get this. Are you ready? We're going back to this raw data, because this is what you got to get used to seeing. and the question says, forecast period 6 with 20% to the most recent piece of data. Oh, by the way, we're using a 2-period. I'm making this up on the fly. 2-period weighted moving average. I want period 6 forecast, 20% on the most recent, 80% on the older. The weights will always add up to 100%. And now you help me through this. That's the whole question. What do I do first? I'm going to start with 0.8 times what?
120.
Huh? Say it again.
120.
125. Sean agrees. Let's go take a look. I said 6. So it's a 2-period. We got to go back to the previous 2 periods. The 80% is supposed to be with the oldest one, which is the 120. I think you said 125.
I changed my mind.
Okay. The oldest one, period 4. All data is in order from the oldest to the most recent. And the future are the bigger numbers. So when it says apply 80% to the oldest piece of data, we know it's these 2 periods because we're forecasting 6. The older of the 2 is the 120. And then we apply 20% to the most recent, which would be the 125. Get it? You want to see another one? Just to make sure? One more? Okay. Again, data will kind of look like that. I don't know where this came from. That's weird. I like it. All right. Let's see. Weighted average. But we're doing a 4-period. And before I tell you which period, I want to put the weights. 0.2 to the most recent. Let's go with 1. That's a point down here. With the oldest. And I don't, what do we got left here? That's a 70, so 0.4. That takes us to 30. That's 0.3. This would be the second oldest. And this would be the other. How's that? There's enough logic there for you to figure this out. You ready? Period we're forecasting is period 9. I want to start with 0.2 times
110. Sorry, 115.
115, I agree, plus point, I gotta find here, I want to go point, let's go 0.4 times, hang on, I gotta look here. 1, 2, how many, what is this, 4 period? 1, 2, 3, 4, okay, what?
120?
I agree, 120, oh, second oldest. Second oldest. Yeah, unless the numbers are the same.
130.
You ready? How are we getting this? Second oldest, how many periods are we looking at?
4.
4. We're forecasting what period?
9.
9. So we gotta go back 4 periods. 1, 2, 3, 4. This is the oldest. Second oldest. Most recent? Whatever you want to call this. Second most recent?
Other, that's your other.
Okay, other, but I mean,
Yeah, it's
on
120.
the test, I gotta call this something. Others, because I'm on the spin here. Others should work. Logical deduction would get you to it, right? So this case, the 20% is with the most recent, which is that 115. The 40% is with the second oldest, which is the 120, not the 125. The oldest, which is the 10%, is times the 120, and then you add to that the, is that where we're at? The 30% times the other, which is what, 130 also? No.
Now, shouldn't the point be 125, 0.1?
21 to go with the 125.
This is, what's old mean?
Oldest.
Oldest? Oh, that should be 120.
25.
Hang on, let me count it off. 1, 2, 3, 4. Okay, you got me. That means this is probably different too.
No, that was right. That was right.
Okay.
There you go.
There should be no problem on the
I feel
final.
like I'm on purpose, right? No, to the left, no, that other place. Okay. 0.3 times other, which is the other at this point?
130.
Okay, thank you. Then you add them. Multiply first, then add last. Multiply, then add. Then, this is the forecast for period 9. Seems like everybody's getting this. These are pretty easy. So, we're all good with weighted total, weighted moving average, and moving average. And those are the easiest. Okay, you're jumping into exponential. You ready? If I give you a smoothing constant, and there's 100%, it's got to be 100% total, you have to tell me the opposite of the smoothing constant, so that when they add together, they add up to 100%. You ready?
The question may say, you do exponential smoothing with a smoothing constant of 0.8, which is 80%. What would be the opposite?
0.2.
0.2, 20%. 0.2. Use a smoothing constant of 0.15. What's the opposite? 0.85. You get it. All right. When you're using exponential smoothing, you're only going to be given the smoothing constant, but you have to do in the calculation both the smoothing constant and the opposite smoothing constant. All right? That's part of the calculation for exponential smoothing, so be prepared for that. I like an example on this PowerPoint, so we'll go same data. There they are. We're trying to figure out if exponential smoothing would work well with this data, so we're going to do as many forecasts as we can with the periods we have here so that we can compare it to the actual. Now here's the deal with exponential smoothing. Let me jump right here. You never count your first forecast in your calculation for mean squared error. Let me say that again because it's only exponential smoothing. Let me say it again. Exponential smoothing, never count your first forecast in the calculation for MSE. Only exponential smoothing is this kind of something that a lot of mistakes get made. Should I say it one more time?
Yes.
Okay. You're going to have to calculate the MSEs with all of these, or be ready to at least. And when you're doing it with exponential smoothing, never, ever, ever count the first forecast in the calculation with exponential smoothing. There's no, it creates bias in your results because there's no real calculation in the first forecast. It's just there to get you started to do exponential smoothing. So here's how you get started. You have to make up the first forecast, and it should always be your whatever your first actual is. Now, let me go to the actual data to make sure I said that right. Yeah, 110. So we look at our first forecast where there's no math involved. We just place whatever the first actual is there, and that's why with no math involved, you can't count it as part of the error because there'd be never a difference. You're actually placing the actual data there. There'll never be a difference between the forecast and data. Now, here's where you get started doing exponential smoothing. Whatever the smoothing constant is, which in this case, the smoothing constant we're going to check here is 0.1, 10%. The opposite is 0.9. You're not told that. You're told the smoothing constant is 0.1. You're supposed to, heard something. You just assume the opposite it would be, because they have to add up to 100%. Okay? You're going to take the smoothing constant times the previous period's actual. Y stands for actual, period 1. You take the opposite of the smoothing constant times the previous period forecast in the second period. It's always the same as the first period. It only happens in the second period, always for exponential smoothing. No matter what the smoothing constant is, your second forecast will end up being your first forecast, which is your first actual. This can count though, because it's not the same as your second actual. This can count as your MSE though, you can count it. Because you did do a calculation to get there. Now watch how it starts to change. They won't line up with actuals from this point on. It's just in that second period. Now we go to period 3 forecast. Previous period's actual times the smoothing constant. Previous period's forecast times the opposite of the smoothing constant. Then add them. What's the actual for period 2 that we're forecasting the 110 for? Period 2 actual is right there, 115. So the difference between our forecast for period 2 and the actual is 5. If you go look at the data, 115 is the second period, or the second period's actual. Now we'll go to the third period. We just forecasted 110.5. What's the third period actual? I can see it right here, by the way. The third period actual is 125. If you go look at the data, now we're getting a big difference now. 125 minus 110.5 is 14.5. And this is what throws, you start to say, wow, that's a big difference. Our MSE could be a little higher on this one, possibly, if you're comparing to some other data. Then you keep going. period 4, again, the smoothing constant times the previous period actual. The previous period actual, for period 3 was 125. The opposite of the smoothing constant times the previous period's forecast. Add them together. There's your period forecast now for period 4. If you look back at period 4's actual, it's a 120. 120 minus 111.95 is 8.05. Not as bad as the second one. It just goes all like that. Keep going, keep going, keep going, until you get to the last possible forecast that you're able to compare to actual data. We only have period 10's actual data. Now, if you decide to use this technique to do your actual forecast, then you go to the next step and start forecasting periods you don't have actual data. We'll go to period 11, and we'll do a true forecast after we know this is what we want to use. Now, if you're looking at exponential smoothing, the bad news is this 0.1 could be any number between 0 and 1.0. I mean, this could be 0.33. This one then would be 0.67. This could be 0.56. This one would be 0.44. And so when you're thinking about using exponential smoothing, you almost got to check exponential smoothing with several different smoothing constants before you even check it against any of these other ones. Because you need to say, well, what if this were being used with a smoothing constant on the low end, 0.1, which puts more weight on the previous forecast than it does the previous actual? Well, what if this is using a smoothing constant of 0.9, which puts more weight on the previous actual instead of the previous forecast? And then you try a smoothing constant that's more in the middle. And when you have this all on a spreadsheet, it's such an easy way to compare 3 different ones. You type in 0.1, click, there's your MSE. Now you type in 0.9, click, there's your MSE. 0.55, click. You can check them in seconds once you have it all set up. And then you keep track of each MSE and go, wow, the exponential smoothing 0.9 was the best MSE. Now I'm going to compare it to other forecasting techniques to make sure which one's the very best for this particular data. Whichever one fits the best, that's the one that's going to be the best to use for your future forecast, because it will most likely have the most accuracy based on historical information, unless you have some kind of economic oddity take place, such as a crash, a housing crash, an economic giant recession starting with a giant thing happening or something like that. When I was doing my forecast, they were like really close until something big happened and then your forecast. You almost have to keep, if you're doing forecast, once a major event takes place, recalculate everything and do new forecasts, taking into consideration what just happened. You almost have to use your judgment to get accuracy until things get back on track again. And then it's unbelievable how you can forecast the future on it. All your budgets start with revenue. You have to forecast revenue, forecast expenditures, and then start subtracting them all. But that revenue is the most important number on all your future budgets. Every accounting office I've ever been experienced with forecast the future at least 5 years, constantly. Every business. They are looking 5 years in the future all the time. And any business I worked with, I had to keep updating it almost every month. I had to go to that spreadsheet and say a month's gone by, that means we only have 4 years and 11 months of forecast, and update it. Now we're back to 5 years. So that's how much is used. Can you do exponential smoothing? Here's another example with a different smoothing constant, 0.8. Notice now it's 0.8 times the previous actual, the opposite, 0.2 times the previous. Notice period 2 turns out to be the same as period 1. That's how it is in exponential smoothing. But after you get past 2, look at how different the numbers are than using the other smoothing constant. They're larger. So putting more emphasis on the previous actual compared to the previous forecast of the other technique, or the other smoothing constant, changed it. Which one's better? 0.8 or 0.1? Let's calculate the MSE for both of them. Here's our actual data. Here is our forecast when we use 0.1. Notice we're not putting period 1's forecast there. We're not using period 1's in exponential smoothing. Here's our forecast. Here's our actual. Here's the difference, squared. And what I mean, I don't see anybody writing notes. Here's the difference, squared. You're not just finding the difference from your forecast to your actual, you've got to square it. 115 minus 110 is 5, 5 squared. Now the next forecast compared to the actual, square it. Let's go to the other smoothing constant. Watch what's happening. This is period 2. There's no period 1 with exponential smoothing. There's period 2. Compared to the 115 is 5, same as the other one. 5 squared. But the next one, the difference is less, squared. The next one, the difference is less, squared. Now let's add up all our squares. Notice we only have differences squared for the amount of forecast that we can compare to actual data. In this case, because we never use period 1, we have 9 of them. We add all the squares and we divide by exactly how many squares we have. This is the key. And then final, I'm looking at people that I know, it happens every year, you'll end up dividing by 9 here, and even though this one is a different technique and only has 7 squares, you ended up dividing by 9 again here, and there's no way you did it right. You're not comparing apples to apples. You have to divide by however many squares you were able to get the MSE, so you're comparing apples to apples. All right? So that division has to be however many number of comparisons you could do with actual data. Now, if I did a forecast for period 11, I mean, that's great, because really that's what we want to forecast, but it doesn't help me with the MSE because there's nothing to compare it to, and we wouldn't even have it involved in calculating the MSE. So you might as well wait until you know which forecasting technique's the best. So, how do we feel? We just learned how to do MSE, but I want to add a twist. You were asked to compare 0.1 exponential smoothing. You were asked to compare 0.8 exponential smoothing. Which, by the way, which one's a better technique? 0.1 or 0.8? 0.8, why?
Lower.
That's right. Lower MSE.
So you said that, like, for instance, at 0.8 was only 7 squared meters. How would we know it was only 7? Is that something that you give us?
Well, you'll say, hey, there's 8 pieces of data, and I can't use the first one, but I'm able to calculate a forecast for the second one through 8, so you're going to have 7 squares here, so you're going to divide by 7.
So 0.1 could have 10 pieces in it, and 0.8 could have...
That's right.
8. Okay.
You're going to use the same data when you're comparing techniques. So if I'm asking you to compare the MSE between whether it's exponential smoothing or exponential smoothing and another one, you're comparing the same data, but another technique may not have the exact same able to forecast. For example,
Okay.
I'm saying use that same data, but I now want you to compare these two to a 3-period moving average.
Right.
3-period moving average, I'm using the same data. Where's my first forecast?
4.
4. We got to jump down here. Here's our first forecast. Now tell me how many squares I'm going to have so I know what to divide by.
6.
Yeah, only 6. You have to divide by 6 then at the end of this one, and not 9. But you're comparing the MSE to that MSE to that MSE because you're comparing apples to apples as long as you divide by the number of forecasts you're able to use. That's the key. That's the biggest mistake, is that people start dividing by the same number, comparing 4 different techniques. I also want you to compare this to a 4-period weighted moving average with the following weight, blah, 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 blah. There's the same data. How many forecasts do you have? I said a 4-period weighted moving average.
5.
How many?
5.
Let me think here. Where's my first forecast? 5. Now I'm going to have one there, there. How many? 6 of them. 4-period weighted moving average was the 4th forecast in period 5. You'll have that many forecasts, which are 6 of them. You'll find the difference to the actual, just like you're doing here. You have another box. You square the differences, you add all the squares up, and you divide by the number of forecasts you had to use this to get the MSE.
So is it always going to be the total minus the amount of periods? So like if you want a 4-period average, we're always going to start at 6. If you want a 2, it's going to be, well, you'll have 8 periods. So is that always going to work?
It's always going to work as long as however many periods you were able to forecast is the number you're dividing by when you add all the differences squared,
Right.
the errors squared. It will work. And you're then comparing apples to apples, even though they're completely 2 different techniques. And whichever one gives you the least amount of error And you would use more than just 10 pieces of data. That's why this is so accurate, is because you're probably comparing this maybe to 100 pieces of data, depending on which technique. When it's on a spreadsheet, it's so easy just to make little changes to compare things. It takes seconds compared to, so it's not that hard. And after a year or two goes by, you don't stick with the same forecasting technique. You reevaluate every technique to determine if the same technique is still fitting the data right. Because data's changed over the time. And so another technique could be better. In my experience, and I usually would always check weighted moving average, exponential smoothing, and trend projection, also called least squares. And trend projection least squares almost always ended up being my best one with almost every data I use. Now, I'm not saying every time, but most of the time, this ended up being my most accurate, best fit. It just happened that way. But I would always test the more complex ones, the weighted, the exponential smoothing, against least squares. The least squares was my most commonly used one. And this, hang on. I went the wrong direction. That is least squares. This looks difficult, but it's so easy. I am going to break this down to make this so easy. Do I have time? Do I have 10 minutes? Huh? I have 10 minutes. This is so easy. Don't let this scare you. That right there means sum of. Okay, sum of. This says n, however many pieces of data you have, times the sum, is that a T? That's a T, right? I think that's a T. Add, take each T for every period, multiply it times every Y, which is your actual data, for every period, and then add all those calculations together. But you have to do all those multiplications first, then add all of those calculations together. Now, let me make sure you understand what I'm saying. You ready? Look at this data right here. And right there. This plumber said, here's how many jobs I've had every month for the last 9 months. I want to use trend projection to forecast the future months so I make sure I have enough parts and supplies in my van based on the amount of jobs I'm expecting, or all the data, whatever it may be. So they set up the data like this and said, I'm going to take these periods and number them 1 through 9, always making the 1 the oldest piece of data, and the whatever the base number is, 9 in this case, the most recent piece of data. So when you get raw data like this, to put it in order, remember, it's always oldest to newest. Then, I'm going to number each one of my periods, 1 through 9, because there's 9 periods there. I'm making the numbered periods, oldest to newest, my T. I'm making the actual number of jobs I've had over those 9 months, my Y. And now I'm multiplying T times Y individually. Do not jump and multiply these two numbers. You will not get the right answer. Individually, each one first. 1 times 353. 2 times that. 3 times that. 4 times that. That whole equation that said sum of T, Y, like this, that is adding those numbers together. There is what you plug in for the sum of TY. The sum of all the T's times all the Y's. That number gets plugged in. You've got to look at that equation as a variable. And what gets plugged into that variable is all these T's times Y added together.
Is that supposed to be a sigma?
It's sigma, yeah. Am I doing it better? Hang on. There. How's that? There. Yeah, it's better Y too. That's what's happening in that equation. So let's go back to this equation now. Right here, this is that number that was at the end of that column. And I always suggest this when I'm doing this part of the lecture. If I were working on a problem that's asking for trend projection, least squares, whatever the words are, I would literally set up my columns and do my calculations straight across And when I get to the bottom and total that out, I just then plug it into this formula. You're plugging a number in there, you're plugging a number there, you're plugging a number there. This little number is how many pieces of, how much pieces of data did we have? How many were there? 9. There's a 9. There's the 17, 14, whatever, 1,000 something that when you add that whole thing up. Here is the sum of all the t's. 1 plus 2 plus 3 plus 4 plus 5 all the way to 9. This is the sum of all your raw data. The however many jobs you had every month, all added together. Now, let's go back. We got our numerator. You ready? I suggest you set it up in these columns just like this. Are you ready? The sum of ty, well, first of all, it says n. N, you said, is 9. Times the sum of ty, 17,844. There's that left side. Then it said plus or minus. Anybody got this PowerPoint on this? Plus? Minus. Minus the sum of t, 1 plus blah, 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 45. You plug in 45 for that sum of t. Times the sum of y, all of these added together, plug in 3,480 for that sum of y. So now we got 9 times 17,844 minus 45 times 3,480. Do the multiplication, subtract, your numerator's done. The denominator. This is very different than this, and I got to emphasize this because no matter how much I emphasize this, somebody is going to put the wrong number. This says the sum of t squared. There's a column called t squared, and at the bottom of that column, that's what gets plugged in there times n. 9 times whatever that is. This is different, even though it looks the same. This is the sum of t, long pause, squared. You're using a different number in a different column here than squared. It's not the exact same as this. Let's go to the data and compare the two. This is the sum of t, which you will square with a long pause, 45 squared. But this is the sum of t squared. 1 squared, 2 squared, 3 squared, 4 squared, add them up. That's the number you plug in for sum of t squared. With no hesitation, the square is trying to emphasize this column. This gets multiplied times 9 minus that squared. That's your denominator. So once you form these columns and get these numbers, it's just plugging them in. And what you're calculating is the slope of the data. You're trying to find, you think your slope, look at the data through time, do you think it's a positive slope or a negative slope? Meaning, do you think our amount of jobs over time are increasing or decreasing? So the slope should be what if we were graphing this? Positive or increasing. And sure enough, we plug those numbers in. Here's our 285, there's our 45 squared times the number, divide this, a positive 7.4, which makes sense because our jobs are going up over time, so it should be a positive slope. That's a good way to check that you did it right. Am I out of time, Casey, to give you that look?
Sure.
Now, your intercept. You've got to use this. I almost spoke too soon. Yeah, you've got to use the slope you just calculated. This represents the mean of y, meaning all of those number of jobs over those 9 months added together divided by 9 to find the average. All of those jobs added to there were 9 months of jobs, there's my average, plug in right there. Minus, now be careful, this is a minus. If this is a negative, this is a minus, a negative, so be careful. But in this case it's positive, so this may, minus, multiply first, your slope you just calculated times your average or mean of t. 1 plus 2 plus 3 all the way to 9 is 45. There were 9 pieces of data. There's our mean of t. So we have the mean of y, which is there, the mean of t, which is there, and our slope, which is there. We multiply these, then subtract them from this. If this is negative, if our jobs were going down over time instead of up, this would have been multiplied, then added, because minus a negative would have been added to this number, and that's a kind of a major mistake, if you make it. So, we now find our intercept. Once you have your intercept, Once you have your slope, you can put any period number here you want. How many pieces of data we have? 9. We want to predict what's the following month. Period 10 would be December. Well, I want you to tell me the forecast for February. What number would you enter in this calculation to give me February? Well, I want you to forecast April. What would you put there? That's what's great about this. Once you have these numbers, you can use this to make forecasts into the future for however long until you go, maybe I should reevaluate this. And then you add, now you have more actual data. You recalculate these. You get your new intercept, or your new slope, your new intercept. You start forecasting into the future, but your numbers are different because you added, because now you have, let's say, 14 pieces of data, and you want to forecast the next period, what number would you use? 15. The next period, 16, right? So this is all about using this crazy formula, which I broke down to make easy, to get that intercept and that slope, then enter whatever forecast period it would be if it were on that list. And you go, if I say, hey, forecast June of next year, you don't have a bunch of, you'll start going, oh my God, I got to change all this. You already have everything you need, except for you're just changing that 10 to what number, if I said, what did I say, April of next year? What number do you switch that to instead of a 10? What, if April of next year were on here, what number would it be? Is it 14? Yeah, January, wait, December, January, February, March, April. 5 plus 9, 14. I shouldn't have to, I didn't mean to confuse you. If I did, you shouldn't allow it to be confusing. So, right, you throw in 14, you just predicted April. Obviously, the farther you go out, though, the less, the more chance you have of it not being as accurate. So you have to, you can only go so far before you go, let's get some more data, then you go farther, then you can keep accuracy. I want to tell you, what you just learned on this one, especially county majors, when you start truly testing these, because you have to work on doing forecasts for budgets or whatever they may be, forecasting revenue, forecasting the number of customers you have, forecasting the number of calls that will come in your call center because you're working at a place that has customer service, whatever it may be, test them. But this is, in my experience, has been the most best fit of any of these that I've ever tested. Sometimes one of the other ones, like social scrutiny, for example, could fit a little better, but in my experience, this has been the one right here. I love this one. I'm in love with this. It's much better than you did. You good? We're all good? We're good? I don't have to do this. I get you all memorized. I know you better than your own parents. You good? All right. One more lesson.